Here we go.
Thank you. Good morning. Last class, we started phase diagrams. We went over some simple one component phase diagrams, and we started on the two component phase diagrams with a simple binary eutectic. So we'll finish up two component phase diagrams today. A diagram with an intermediate compound, diagrams with solid solutions, and then diagrams with liquid immiscibility. And then on Wednesday, we'll do ternary phase diagrams, and that'll be it on some of the basics. And then next week, we'll start on the refractory compositions. So this is a phase diagram with an intermediate compound. So A and B are the two endpoints, and then the compound here is just AB2. It could be any combination of A and B, but this one happens to be AB2. So this one's in mole percent, and here is the phase field for A plus AB2. AB2 plus B is the second phase field with two solids, and then you have four two-phase fields, A plus liquid, and then these two are AB2 plus liquid, and then B plus liquid. So basically, this vertical line is AB2, and if you look at the diagram to the left of AB2, it's a simple binary eutectic, and then the one to the right of AB2 is another simple binary eutectic. So if you follow AB2 composition along this line as you're increasing the temperature, it's a congruently melting compound. So AB2 melts directly to a liquid of the same composition of AB2. So this is congruently melting compound. I've already mentioned that if you separate this into two phase diagrams along this line AB2, you basically have two binary phase diagrams. One is A, AB2, and the other one is B, AB2. So when you have a simple diagram like this with a congruently melting compound AB2, you can separate it into two simpler phase diagrams. So this is the phase diagram for MnO Al2O3. There's one compound here, MnAl2O3, which is abbreviated Ma. So you have a binary, simple eutectic binary, Al2O3, and then Ma, and another simple binary, MnO, Ma. So we'll take a composition at X that's 35% Al2O3, and then 65% MnO. So we'll just look at what happens when we cool this composition X. And I just put this on here to calculate the percentages for this compound MnO Al2O3, which is Ma, or on this diagram, or MnAl2O3, this vertical line, which is about 59% Al2O3 and 41% MnO. So I just put down the atomic weights here, and I just calculated that. So the atomic weight of Mn, 54.94, the atomic weight of oxygen, 16. So you add those two together for the formula weight of MnO. So that's 70.94. Then the atomic weight of Al is 26.98. So Al2O3 is 2 Al and 3 O. So it's 2 times 26.98. and then 3 times 16 for oxygen, and that's 101.96. So the weight percent of Al2O3 is just 101.96 divided by the sum of these two, 70 and 101, so that's 172.9. So 59% alumina, and the manganese oxide is 70.94 divided by 172.9, or 41%. So that's what we have here, 59% alumina and 41% MnO. And again, a mole is this number, 6.022 times 10 to 23 of a chemical unit. That could be atoms, molecules, ions, or whatever you want it to be. So X is 35% alumina and 65% MnO. And then Ma is 59% alumina and 41% MnO. So as soon as we cool this composition X, we run into the liquidus curve right here. So this point, if you look at the temperature axis, is about 1670 degrees C. So if we're just above this temperature, we have all liquid present. And as soon as we drop below the liquidus temperature at 1670, we'll start to crystallize Ma. So as we go below 1670, crystals of Ma begin to appear. And again, Ma is just MnO Al2O3. The crystals have this composition. It's always the same, 59% Al2O3 and 41% MnO. And the liquid has this composition right here, 35% Al2O3 and 65% MnO. So then we drop the temperature down to 1560. This tie line here is about 1560. And now we have a great deal more of the Ma crystals appearing. So again, the composition is of X is 35% alumina and 65% MnO. And then this tie line is 31%, and this portion of the tie line is 23%, and this portion is 8%. So we take this tie line, 31% at 1560 degrees C. We're connecting the liquid and the crystals Ma. Now, the liquid now has this composition. You drop the vertical line. It's about 27% alumina and 73% MnO. So the amount of liquid present, again, is 27% Al2O3 and 73% MnO, is this portion of the tie line, 23, which is opposite the liquid phase, divided by the total, which is 31. So 23 over 31 is 74% liquid. And then the percent solid is this ratio. 8 is opposite the compound Ma, so it's 8 over 31, or 26%. And again, Ma is always 59% alumina and 41% MnO, but the liquid composition keeps changing. So that's at 1560. And then if we drop it down to just above 1520, which is the solidus line. So at 1520, let's call it plus, just above 1520, we have a great deal more crystals of Ma appearing. So the tie line at 1520 plus goes from the eutectic to the crystal Ma. So we're connecting a liquid to the solid Ma. And now the liquid is the liquid at the eutectic composition, 25% alumina and 75% MnO. So if we do the math here, the percent liquid for this composition, 25% alumina, 75% MnO, is just 23 over 33, or 70% liquid. And then the percent solid is 10 over the entire tie line of 33, or 30%. So just above 1520, there's still 70% liquid present. So when we drop below 1520, all the liquid disappears. We'll call that 1520 minus. And now we have two crystals present, MnO and Ma. So the tie line is the same tie line just below 1520. We're connecting the eutectic with this compound Ma. So the percent solid of this eutectic composition, which is this here, 25% alumina and 75% MnO, is the tie line 23 over 33, or 70%. So there's 70% of the eutectic solid, which consists of 25% alumina and 75% MnO, and then the percent solid of Ma, which is this composition here, 59% alumina, 41% MnO, is just 10 over 33, or 30%. So now you have 30% Ma and 70% of this eutectic composition, which consists of these two percentages, 25% alumina and 75% MnO. So here's the same phase diagram, a little simpler. And then we want to determine the eutectic proportions of the MnO and the Ma. So this tie line is going from MnO all the way over to Ma. And this portion of the tie line is a proportion of Ma over the total tie line. And then this proportion of MnO is this part over the entire tie line. So the amount of Ma in this eutectic composition is 25, which this is 25% over 59. So the entire tie line is 59%. So that's 42% Ma. And then the proportion of MnO is 34. This is 34% over the entire tie line of 59%, or 58%. So when we cool down through the eutectic at 1520 degrees C, the liquid crystallizes to MnO and Ma, MnOAl2O3. So when we're at composition X, we first start crystallizing Ma in liquid. So we're generating Ma crystals. So the microstructure looks something like this. We have these crystals of Ma that are forming in a liquid matrix. So crystals of Ma form above this solidus curve, 1520 degrees C. And then when we get to the eutectic, we develop one of these layered type structures, alternating layers of Ma and MnO, and that's below 1520. So this is what the microstructure would look like: the initial crystals of Ma that first form, and then the alternating crystals of Ma and MnO. That was a phase diagram with a congruently melting compound. And here's another phase diagram. This one happens to be V2O5 and Cr2O3. This is a refractory material. The vanadium oxide is a highly undesirable compounding connection with Cr2O3. It usually comes in as an impurity in a fuel, and it really lowers the melting point of the chrome oxide. You can see how low these compounds are here, less than 800 degrees C. So this is an incongruently melting compound. So you have V2O5, Cr2O3, and the compound here is Cr2O3, V2O5. So this is in mole percent. Phase diagrams are either in mole percent or weight percent. This is in mole percent, so it's a one-to-one compound. So an incongruently melting compound melts to a liquid of different composition and a different crystalline compound. So as you increase the temperature at this one-to-one ratio, Cr2O3 V2O5 transforms to Cr2O3 plus liquid. So it's a different crystalline phase and a different, it doesn't melt directly into a liquid of this one-to-one composition. The liquid composition is over here at this point P, which is the peritectic reaction. So as you increase the temperature, this goes to Cr2O3, a different crystalline compound. The Cr2O3 V2O5 disappears, and the liquid is not of this one-to-one ratio. It's over here at this point P. So we did a congruently melting compound, and this is an incongruently melting compound. So P is the peritectic point, and then this tie line from P to N, it's at 810 degrees C. These are equilibrium phase diagrams. So along this tie line, you have Cr2O3 V2O5, you have that one-to-one compound, you have Cr2O3, and then you have a liquid. So they're all along this tie line, they're all in equilibrium. And again, at this one-to-one ratio, this compound, Cr2O3 V2O5, transforms into just the chrome oxide Cr2O3 and this liquid. So if we look at X, this composition X, and we can cool down and see what happens. So these are isoplasmal studies, just these cooling studies. So we're looking at composition X at the liquidus line right here. So you have Cr2O3 crystals forming right here. Then if we go down to this solidus curve here, it's actually a solidus curve, but it's also a liquidus curve over here because we have a solid and a liquid. Here we have two solids. At 810 degrees C, the Cr2O3 disappears, and we form this one-to-one ratio of Cr2O3 to V2O5. And the liquid composition at X does not change, it's still P. This is a very short tie line between P and the one-to-one compound. So when we're going through this transformation where we start out with Cr2O3, and then we're crystallizing this one-to-one ratio of Cr2O3 to V2O5 along X there. we first crystallize Cr2O3, and then we're trying to crystallize Cr2O3 V2O5. So if the cooling is too rapid, you get something known as coring. So you're no longer at equilibrium. You're going to have these Cr2O3 crystals surrounded by this liquid, which transforms to Cr2O3 V2O5. So if you cool too rapidly, you're not going to reach equilibrium. And that's because atoms have to diffuse across these interfaces. So you have Cr, V, and O atoms that have to diffuse. This is in the solid state. This may still be in the liquid state, but when you have all solids, the diffusion is even slower. So rapid cooling, you're no longer at equilibrium, and you'll get what's called coring crystals of Cr2O3 that have not transformed to the equilibrium crystal Cr2O3 V2O5. So that's why when you make phase diagrams by holding different compositions at temperatures for a long time until you reach equilibrium, you have to do that to end up with a phase diagram because they're all at equilibrium. So rapid cooling, you're not going to reach equilibrium. So you end up with something that looks like this. So this is the same diagram, V2O5, Cr2O3, and now we'll just look at another composition Y and cool down along this composition Y. So at the solidus line over here, 810 degrees C, you go from the Cr2O3 solid plus liquid to Cr2O3 solid plus this one-to-one compound. So you're forming both of these crystals at this location Y. If you're at this composition, the one-to-one ratio, so one-to-one V2O5 and Cr2O3, when you're done cooling, you're only going to end up with the one-to-one compound Cr2O3 V2O5. So there's various types of these binary phase diagrams with an intermediate compound. And I have 3 or 4 of them to show you here. So we have A and B are the end members, and we have some compound, in this case it's A2B3 over here. So this is an example of a phase diagram with the decomposition. So as we increase the temperature here, we have this reaction taking place. So here is A plus A2B3, and then B plus A2B3. So as we increase the temperature, we reach this horizontal line. A2B3 decomposes to A and B. So that's a decomposition reaction. And then you can see at this point in the upper part of the phase diagram, you have a simple eutectic phase diagram. So that's an example of a decomposition. Here's an example of a stability region. So A and B are your endpoints again. There's a compound AB that forms, and it's only stable between 2 temperatures, T1 and T2. So AB is stable between T1 and T2. So in this region here, A plus B form AB2, and then A plus B form AB, and then AB decomposes again at T2 to A plus B. So there's a compound that's only stable over some temperature region. And then this is a phase diagram with a phase transformation. So this is common in quite a few of the refractory phase diagrams. So A and B are your end members, and here's the compound A2B. So this region is A plus beta A2B, and this region is B plus beta A2B. So in this part of the phase diagram, A2B is in the beta form, beta crystalline form. And then at temperature T2, it transforms, and this is going to be a displacive transformation to alpha A2B. So A plus alpha A2B or B plus alpha A2B. And then you have your normal a simple binary phase diagram over here and another simple binary phase diagram over here. So this is an example of a beta to alpha phase transformation. Here's another example of a phase transformation. So there's only two compounds on this simple diagram, A and B. So below T3, you have A plus the beta form of B, and then above T3, you have A, and now the beta form transforms to the alpha form. So it's another displacive transformation between two crystal structures, alpha and beta. So the solid solutions are pretty common in refractory materials. So there are three possible reactions when a melt of multiple components, and these are just showing two here, two or more kinds of atoms are cooled. So there's two atom types here, an open circle and a crosshatch darker circle. So this is the melt of two different kinds of atoms, it's a random arrangement. So one possibility is you develop two crystalline phases. The open circles are one phase and the crosshatch circles are another phase. The second is these two atoms form a binary compound. So they're in an ordered crystalline lattice. And then the third possibility is a solid solution. So we're just showing a substitutional solid solution where the darker crosshatch atoms, the circles representing the atoms, are substituting on the other sites where we have the open circles. So it's a direct substitution of this crosshatch atom on a site that used to be an open circle. So the solvent atom is the greatest concentration. That would be the open circles here. And the least concentration is the solute atom. That would be these circles there, the darker ones that are cross-hatched. The solutes are going to be the lower concentration. So there's really two types of solid solutions here, a substitutional solid solution and an interstitial solid solution. So I just showed this one, the substitutional version, where there's a direct substitution of the crosshatched atoms on the lattice sites for the other atoms represented by the open circles. So the solute atom just fills a lattice position normally occupied by the solvent atom. That's a substitutional solid solution. There's also an interstitial solid solution. So these atoms would be smaller. They would be substituting in these interstitial positions. So the solute atom simply fits into the interstitial positions of the solvent atom. So there's a substitutional solid solution and an interstitial solid solution. So how does a solid solution form, well, there's four different reasons. First of all, you have to consider the size. The solute atom should be about the same size as the host solvent atom. So if the difference is greater than 15%, there's going to be very limited solid solution forming, limited substitution. So if the difference is less than 15%, you have a good chance of forming a solid solution. Chemical affinity. If you have strong chemical affinity between the solute and the host atoms, the solvent atoms, you're probably going to form a compound. And that's really going to limit the amount of solid solution that forms. The charge on the atoms is also important, so the valency. So ideally, a solute atom should be the same charge as the host atom. So the valences should be the same. And then the crystal structure, the solute and the solvent atoms should have the same crystal structure. So if they have the same size, low chemical affinity, the same charge, and the same crystal structure, you're probably going to form a solid solution. So nickel oxide and magnesium oxide form a complete solid solution. Both have the cubic crystal structures. Both have valences of +2, so Ni is +2 and Mg is +2. And both have similar sizes. So there's a less than a 6% difference in the size of Ni and Mg. So the atomic radius of Mg is 0.65 angstroms, and the atomic radius of nickel Ni is 0.69 angstroms. So they're almost the same size, same charge, same crystal structure. So they form a complete solid solution. So this is what a solid solution phase diagram looks like. Temperature, and then we have the composition in mole percent. So this is 100% MgO. That's the higher melting point. It's a very useful refractory material, around 2800 degrees C melting point. And then this is 100% nickel oxide that melts at about 2000 degrees C. This upper curve is the liquidus curve. The lower curve is the solidus curve. So below the lower curve, we have a complete solid solution. Above the liquidus curve, it's all liquid, and in between, we have a combination of solid solution and liquid. I wonder why that went backwards, but this is an example of CaO, MgO. It's a partial solid solution. So this is not a complete solid solution like for the nickel oxide and the magnesium oxide. It's a partial. So both of these materials, CaO and MgO, they're both cubic crystal structures. They both have a charge of +2 at Ca +2 and Mg +2, but now they have different sizes, and it's greater than 15% difference. So the atomic size or radius of Mg is 0.65 angstroms, but Ca is much larger, 0.99 angstroms. So that limits the amount of solid solution. So this is what a phase diagram looks like with a partial solid solution. This is MgO 100% and CaO 100%. This one's in weight percent. This region right here is MgO solid solution. So this is a limited region where a small amount of lime is dissolved in the MgO to form a solid solution. And then this region here is CaO solid solution. So there's a small amount of MgO dissolved in the CaO in this region. And then this large region in the center is your MgO solid solution plus CaO solid solution. So there's some Ca dissolved in MgO, some MgO dissolved in Ca. And this is a very refractory material anywhere on this phase diagram. You can see 2370 degrees C is where the first liquid forms. MgO CaO is actually from the dolomite mineral, the solid solution of the calcium and magnesium carbonates. So here's again a complete solid solution for nickel oxide and magnesium oxide. And we'll just take this composition X and see what happens when we cool it down. So that's at 40% MgO and 60% NiO. So we'll just follow this down as we cool it and use the lever rule. So above this temperature, which is about 2430 degrees C, we just have a liquid phase present. So we're just above this liquidus line. And as we go below 2430 degrees C, we start to develop crystals of the solid solution. So this composition here is 63% MgO and 37% NiO. And then this composition is 40% MgO and 60% NiO. So this is the liquid composition. This is the solid solution composition. So if we go down to even lower temperature, 2350 degrees C, we're right here. It's about 2350 degrees C. This point is now 30% MgO and 70% NiO. And then this point right here is about 53% MgO and 47% NiO. So this is a liquid composition, and then this is the solid composition. So liquid composition and solid composition. And this is, again, a solid solution. So at 2350, at this temperature, the tie line is connecting the liquid to the solid solution. So the percent liquid of this composition, 30% MgO and 70% NiO, is this tie line portion 13, which is opposite the liquid phase, divided by the total tie line, which is 23. So 13 over 23 is about 56% liquid of this composition. And then the solid solution of this composition, 53% MgO and 47% NiO, is this portion of the tie line 10, which is opposite the solid solution over 23. So 10 over 23 is about 43%. So at X, at this temperature, we have about 56% liquid and 43% solid solution. And then at 2250, we're right here. We're only going to have a trace amount of liquid present. And that's 20% MgO and 80% NiO. And then this composition is the solid solution is 40% MgO and 60% NiO. So now the liquid phase has disappeared at this point right here, and we're just entering into the solid solution region. So below 2250 degrees C, there's no changes occurring in the equilibrium solid solution, which consists of 40% MgO and 60% NiO. So that just continues down as the same composition solid solution as we keep dropping the temperature. So here's our solid solution that first forms as we just cross the solidus line. So the first solid solution crystals are rich in MgO. And then as the temperature is lowered, the solid solution crystals that form are less rich in MgO. So what has to happen is nickel has to diffuse into these first crystals that are MgO rich, and then the Mg has to diffuse out and into the regions that are richer in nickel. So if it's, again, a situation, if it's cooled rapidly, you're not going to be at equilibrium. You're going to have regions of solid solutions that are at different ratios of MgO and NiO. So again, phase diagrams are at equilibrium. So if we were cooling down, we'd have to hold these at long temperatures to allow diffusion, at long times at temperature to allow diffusion to take place and reach equilibrium again. So we have a compositional gradient in a solid solution due to slow diffusion rates at lower temperatures, and this counter diffusion of Mg and Ni isn't going to take place, and we won't reach equilibrium if we cool too fast. And then the last item here is liquid immiscibility. So there are phase diagrams where we have these liquidus domes, where we have two liquids present that don't dissolve in one another. So we can have two separate liquid phases. So here's the binary phase diagram, A and B. This dome here is two liquids that are immiscible. So the region MST is the two liquid region. It's L1 and L2. So two liquids that don't dissolve in each other. So if we look at this composition line X and we cool it down, we're above this curve here, the liquidus curve. We just have one liquid phase. But then as we cool down and we reach point S, two liquids appear, L1 and L2. So in this dome, we have two liquid compositions that each liquid doesn't dissolve in the other one. So here's a tie line. This dotted line, this horizontal dotted line is a tie line. The left side that intersects the liquidus curve is the composition of L1, and the right side of the tie line that intersects the liquidus curve is the composition of L2. So you just follow these vertical lines down that I put on the diagram. So A is the composition of this point A. I put it in red because it's not the it's not the compound A, it's the point A. That's the composition of L1, and then B, this point is the composition of L2. So if you do the tie line ratios, XB, this is XB divided by AB, the entire tie line. That's the percent of L1. And then the percent of L2 is the shorter tie line AX over AB. So there's a lot more L1 present at this temperature and this composition X. You keep cooling down, you reach this point R, and then you're going into this region A plus L2. So L1 disappears, A crystallizes out, and you still have L2 present. So these two immiscible liquids, there's two growth mechanisms for this phase separation. One is a nucleation and growth, and one is a sphenoidal decomposition. So you have two liquids present, composition would be A and B. So the vertical direction is composition, and the horizontal direction is distance in that melt. And M is the composition somewhere between A and B, the composition that we're looking at. And as we're going from top to bottom in these diagrams, we're increasing the time. So we start out with two liquids, A and B, and then B is in greater excess. So B starts to nucleate and crystallize. So it's a nucleation and growth process. And the arrows here represent the way these crystals are growing. So B keeps getting larger until all the B is consumed. So we have B, and then we have A. So we have a certain amount of B crystals and a lesser amount of A crystals. So we have two crystal phases that nucleate and grow. In the sphenoidal composition, there's a gradual change in concentration. There's no nucleation and growth process. And in this case, the arrows are indicating the increasing concentration of B at these maximum points on this curve. And that in this sphenoidal decomposition, the concentration just keeps increasing. So the concentration of B is increasing in these regions here until finally B crystallizes, and here's the percent of B that crystallizes, and then A. So we have the same result, basically. We have crystals of B in greater concentration than crystals of A in both nucleation and growth and sphenoidal decomposition, but the microstructures are not the same. They're totally different. So if we have nucleation and growth in from our two liquids, and small spheres are going to nucleate and grow. So the first compound that crystallizes out in our case was B, and then A crystallizes out and forms a matrix. So isolated crystals in a matrix is basically what a nucleation and growth process would look like. And then the sphenoidal decomposition, because it's a gradual change in concentrations, are going to give rise to this interconnected microstructure. So this could be the A phase, this could be the B phase. You can see how they're basically a continuous, each one is a continuous phase in the other one. So totally different kinds of microstructures. So liquid immiscibility certainly shows up in some of the refractory systems. This would be a silica type refractory with lime additions. And small lime additions are used as mineralizers in silica refractories to enhance the rate of crystallization of tridymite and cristobalite. So this is a portion of the SiO2 CaO phase diagram. This is only 30% CaO, and this is 100% SiO2. And the temperature goes from 1600 to 2200 degrees C. So here's your two liquid phases in this dome here. So above this dome, it's all liquid. In this dome, it's two liquids. And then below 1698 degrees C, silica starts to crystallize, either tridymite or cristobalite, and then you still have your liquid phase. So here's an example of a refractory system with two immiscible liquids. Another one is MgO SiO2. Magnesium silicates, especially phosphorite, are important refractory materials, and by themselves and also as second phases. So a phosphorite could be a second phase, the magnesium silicate could be a second phase in an MgO refractory. So this is 100% SiO2, and this looks like about 35% MgO from 1600 to 2200 degrees C. Your two liquid region. And when you see a phase diagram with dotted lines, that's an estimate of what somebody thinks is going to happen. These lines, the solid lines, are actually lines that were determined by experiment, but the dotted lines are extrapolated. But there's a two liquid phase field here, a liquid phase field, and below 1695, silica will crystallize out and you'll still have a liquid phase present. So that finishes what I have today. Wednesday, we'll go over the ternary phase diagrams, three component phase diagrams. They're more complicated. So we'll finish that on Wednesday. So again, if you have any questions, just send me an email or you can always interrupt during the class. So have a good rest of your day, and I'll see you on Wednesday again. Thanks.
Thank you.
Thanks.